Okay. All right. So we're going to start looking at refraction of light. So we've talked about reflection. Refraction is, well, the definition here is the bending of light as it travels from one medium into another medium. So I have mentioned this a few times before with the different mediums. So as you can see here, the pencil in water. And may I suggest actually doing this at home, just to kind of put to terms what we're kind of talking about here. So what happens is, without talking about the pencil first, when light travels, and it has a speed, 3.0 times 10 to the power of 8 meters per second, okay? So it has a speed that it travels. That is the speed it travels. That is the fastest speed that light can travel, okay? And we're going to get to an equation later where we use that that one a lot, the 3.0 times 10 to the power of 8 meters per second. And that is our constant because that is the fastest that light can travel ever. So that is the fastest light can travel, and that is in a vacuum, okay? And I could say not an actual vacuum, but space. So we base everything off of that, okay? It will never travel faster than that, okay? It travels slower. So what we're going to start looking at is finding the speed of light when it is traveling through water or traveling through glass, okay? That is the next step to looking at this. So we're going to do calculations to find the speed of light when it travels through other things. So one thing we had talked about is, that light, everything is reflecting light off of it, right? Unless it's black, it's absorbing it. But because it's reflecting light off of it, that is what it's allowing. That's what allows us to see things. Unless you're in darkness and you can't see anything. That's the absence of light. So there's no light that's being able to creep into your eyes. So what happens here is that when light is being reflected off the pencil in this picture here, it is being reflected off the pencil. And what happens is it's traveling at one speed when it's in the water. Okay, so light has bounced off the pencil. It's traveling at one speed when it's in the water, but when it gets to air, it speeds up. Okay, and what happens is when it speeds up, as soon as it leaves the water, the angle that it left the water is going to change. So it's not going to leave the water straight. It's going to bend to one side or another, and it's going to cause an angle, whether it slows down or whether it speeds up. It's going to depend on that, which side it goes to or which angle is created. That would be better, make more sense. So when it changes the direction and it still comes in, it hits us in the eyes, we're going to see the pencil where that light, that reflected ray sped up, so left the water. Okay, so when it leaves the water, it speeds up and the angle of it changes. And that's where we're going to see the pencil in the water. Okay, our eyes can't handle that change of direction. Like our brain, it's our brain. Our brain can't handle that change of direction. So we see things in the direction that the light hits our eyes. And I've mentioned that that's where mirage is coming from, right? The light rays that are leaving things are changing because of the heat the cold and the heat, and so the angle of which is hitting our eyes at a different spot. So then that's the mirages have the same sort of aspect where it's the direction has changed, and that's why we see things. So when light travels from one medium into another, it's either going to speed up or slow down, and it will bend. It will. I'm not saying it's going to bend into a circle, where it's going to create an angle, let's say. And then that light rays hit our eyes and we see the object at whatever angle that light ray is hitting our eyes. So in this case, we're not seeing the pencil where it actually is. Okay. Hopefully that makes a little bit of sense. So we're going to scroll down here. Okay. In the diagram below, the light. Okay. So here, this is perfect. Okay. So in the diagram below, the light ray is traveling from one medium to another. The incident light energy is split between the reflected ray and the transmitted ray. As you can see, the transmitted ray changes direction. This is refraction because it's bending. So it's not like curving, it's bending. So just follow my little arrow here, okay? So this is the incident ray. So this is coming from our light source. So the light ray is coming, okay? And the background is showing two different colors because it's two different mediums. So it's going to hit this other medium. And you can see here that the angle from, this is see the normal down the middle. So this is where we're going to, wherever the light ray hits the medium, you're going to draw that normal up perpendicular from it. So you can do that whole angles here. This angle is a lot bigger than this angle. So that refracted ray, it bent away. Okay, and you'll get comfortable with this, but this means that the light sped up. So it got faster, which means what would make sense is that this one up here could be water. The light's traveling through water, say from the pool light. Okay, and as soon as it hits the air, that light ray is speeding up. Okay, so we have that little angle, the little theta I and the theta little r there. That's the angle of incidence, angle of reflection. This one is a little theta with a capital R. That's to represent your angle of refraction. Okay, so this is just to give you a blurb here. So if theta r is bigger than theta I, okay, so if that refracted angle is bigger than the incidence angle, the light bends away from the normal. Okay, that means that means the light has sped up. So you can see here, this one's bigger, which means the light got faster. So this is probably air, and this was like water. Okay, and then if the refracted ray angle is less than the angle of incidence, so if this here, this refracted ray had got closer to the normal, maybe went down this way, that means that the light slowed down. Okay. This is something you really need to practice just to kind of understand it a little bit, okay? Not something to take not lightly. It's not like it's super serious, but it is something that you do need to practice. It's a skill. These are skills. It's not memorization. It's understanding, okay? There is no memorization in this. It's just understanding what the light is doing. So light is fast as in a vacuum. So traveling at 3.0 times 10 to the power of 8 meters per second. Symbolically, this number is C, okay? C stands for constant. So we're going to talk about index of refraction. This is like a rating scale or like a ratio. Index of refraction are, so here it says a number that communicates how slow light travels in a medium compared to C, okay? So this is how slow light travels compared to C, which is the fastest that light can travel. So we are going to use C as our starting point. So C is 1. 1 is the fastest light can travel. 1 is a vacuum, okay? Even air is just slightly slower than a vacuum. And we have a whole little chart down here. So index of refraction for a vacuum is 1. That is the fastest that light can travel. Light in air is 1.0003. Light in carbon dioxide gas, I didn't say 1 up there, but that's okay. 1.0005. In water, it travels at a 1.33. Alcohol, 1.36, and so on. We don't need to go over every specific one. Math here. We're using this equation, okay? So C is our constant. That is the speed of which light can travel the fastest. N is our index of refraction. Velocity is the speed of light in something else. So say we want to know what, let's look here. Plastic, maybe like a plastic. Say we wanted to know what a plastic would have on this rating scale. So just so you know, I'm going to tell you right now, you won't get anything above 3 maybe it will give you some questions that you might get a 3-point something, just as, practice questions. But all the numbers are pretty much between 1 and 3. Yeah. Maybe, yeah. 3, 1 and 3. That's the numbers, the rating scale for the index of refraction. So say we had a substance and we wanted to know how fast light, we wanted to know what the index of refraction is for it. We wanted to know where it would fall on the rating scale, right? Does light travel faster in the plastic or faster in the plexiglass, right? So we don't know what the index of refraction is for it, but say we measure the speed of light in it. So we would measure the speed of light in this plastic and you'd put it here. And then you would put it compared to the constant. And that is going to get you your index of refraction, which is like your ratio of how fast light can travel in that substance. Okay. So again, it's just like the magnification questions. It's just like those electricity, the Ohm's law questions, all the same, right? Just 3 variables, just practicing manipulating those variables. Okay. So we have an example here. I'm just going to write the example down, and then I'm going to flip over to my camera here so that we can kind of do this together. Speed of a sample of glass. Okay, so you should be starting with writing down your givens, right? So we have a speed of light in a sample of glass. So that's going to end up being your V. Okay, so what I just explained to you, like we don't know what the index of refraction is for it, but we have the speed at which it can travel. We have the speed at which light can travel in it. So in this random sample of glass, the speed is 1.19 times 10 to the power of 8 meters per second. Okay, now we have 3 variables in this formula. Okay, you're only ever going to have to look for N or V because C always stays the same. Okay, so you're never going to have to isolate for C. You're never going to have to guess what C is. We always give you C, but after a while, you'll end up memorizing the fastest that light can travel. And you will, you only have to find the other ones. So I'm just going to, let's see, what if I can figure this out? Stop presenting. And then if I can do the hover cam now. I don't think I can. Let's see. Give me a second. All new for me. You can try to figure out the answer before I get to it. Did it work? Can I present that? Let's see. I can. Okay. Yay. All right. I figured it out. I'm getting better. Okay. So we have our speed that light travels in that sample of glass. We have our constant. Always stays the same. Never changes. All you got to do is fill them in now. Is do the 2 zeros. I always end up just doing 1, but that's just because I'm lazy sometimes. And we have 1.19 times 10 to the power of 8 meters per second. Okay. And again, just as a little tidbit of easier way to do it, if you are not comfortable with the putting on all of the scientific notation, you can just cross this off here because they are the exact same, right? I know you can't see that very well. I'm sorry. Cross that off. And then all you have to do is do your 3.00 divide by 1.19, and you get a 2.52. And just so you know, index of refraction has no units. So that just stays 2.52. I can't tell you how many kids will throw these on it. Do not. Index of refraction does not have units, and the number should fall in between a 1 and a 3. Okay, so if you've done it, if it falls in between a 1 and a 3, then you've done it. You should have done it pretty much right. And we don't throw any units on it. Okay, so for this now, you're going to go and you're going to do some of the questions there on the practice sheet. And I will put in the news feed which questions I want you to do so that you don't have to do them all, but at least attempt to do a couple of them. And I will make sure that you do a couple of them where you have to solve for n and v, so then you can practice rearranging that equation. And that is it.